Great pleasure to be here. Thanks for inviting me. So I want to talk about something that I've been thinking about for the last 3, 4, 5 years, and that is to try to understand the security of sort of cryptographic systems that we use all the time in practice, and yet we understand very little. So hopefully I'll tell you a little bit about where we are at. This is joint work with Tianren, who was a former student at MIT, Angelos Pelecanos, who was also a former student at MIT, and Stefano Tessaro is due up. All right, so what better way to start a talk than going all the way to the very beginning? Is quote of by Alan Turing, who says this. I mean, you can all read it, right? So he says roughly that he has this little program that he set up on this computer of the olden days, and he says, look, this computer does the following: takes a 16-digit number and outputs another 16-digit number. That's all it does. Okay, and he says, look, you have access to it. You can ask it as many questions as you want. I challenge you to predict what answer it'll give on a new 16-digit number. Okay, this is a pseudorandom function, and this is an unpredictable function, really very closely related to pseudorandom functions. Okay, so this notion was formalized in this amazing work of Goldwasser and McCulley in the 80s. So what it is, again, is a bit more formally is a small collection of functions or permutations for that matter, right? That maps n bits to n bits. The function is described by a k-bit key. You should think about k as polynomial in little n, right? So the total number of functions is the total number of keys, which is 2 to the polynomial in n, right? Yeah, this is how it works. And what you want is that you give a polynomial time algorithm, a distinguisher, access to this function or some other function. Okay, so the distinguisher lives in one of two worlds: either the pseudorandom world, where it gets access to a random function chosen from the family. In other words, you pick a random key, defines a function, give them access to it, and they can query it on any input and get the answer. Or the random, or a truly random function from n bits to n bits, of which there are 2 to the n, right? Roughly speaking. Yeah. So on the one hand, you have 2 to the poly n functions. The other hand, you have 2 to the n functions. And pseudo-randomness says that nobody can distinguish between the two worlds. No polynomial time algorithm can distinguish between the two worlds. Right? That is the notion of pseudo-random functions. The extremely influential idea. The influence extends well past cryptography into learning theory, natural proofs in complexity theory, and so on and so forth. Okay, so the key question that I will address today is, how do you build pseudorandom functions? How can you construct such small function families which are nevertheless indistinguishable from random functions? Yes. Prayesh, hey. I should have guessed without, yeah, okay, go ahead. Yeah.
So the brief question was about prediction.
Yes.
Suppose if you can distinguish from random, then you can just also predict by the standard boosting type thing.
So one way is easy, right? If you can predict, you can distinguish. But if you can construct an unpredictable function, you do a Goldreich-Levin, use Goldreich-Levin to turn it into a pseudorandom function. So I'll sort of treat them as both roughly the same thing. We've moved past Turing and we are in the GGM world, right? All right, so how do you build pseudorandom functions? And here the answer couldn't be more complicated in a sense. I mean, there are two different sets of people whose job it is to construct, who are sort of preoccupied with constructing pseudorandom functions. One is theorists like ourselves, and the other one is sort of people who build these things in practice. Okay, and they do completely different things. They look at completely different constructions. One has proofs, the other one doesn't. Things couldn't be more different. Okay, and I'll tell you more about it in a second. In theory, we have beautiful constructions. So this is the GGM construction of a pseudorandom function family from a pseudorandom generator, which just stretches from n bits to twice n bits, right? How many of you among the students have seen this construction, just as sort of a calibration? Not that it would matter for today, but okay, cool. If not, you should. right? This is sort of a construction from the book. You really should see this this construction and its proof. And again, combined with another amazing theorem of Hastad, Impagliazzo, Levin, and Luby, who construct pseudorandom generators from one-way functions, we know that one-way functions are sufficient necessary and sufficient, it turns out, to construct pseudorandom functions. So this is what we know. Right? So you could take a sort of a natural one-way function that that follows from the hardness of factoring numbers, right? Plug it in to Hill, Hastad et al. And then plug in the generator you get to GGM, you get a pseudorandom function. That's it. There are more direct constructions. For example, Nauer and Reingold came up with this beautiful construction that relies on the hardness of the Diffie-Hellman problem, so-called decisional Diffie-Hellman, but never mind. And if you want, for some reason, a permutation, so not a function family, but a one-to-one onto bijective function family, you can also do that. The general theorem of Luby and Rakov, inspired by a construction of Feistel from the 60s, that says you can take any pseudorandom function family and construct a pseudorandom permutation family. Okay, so it's a beautiful sort of edifice of theory, most of it built in the 80s that we know about this object. Now, the way you sort of you gain confidence in the security of these constructions, right? The no distinguisher can distinguish, etc., is via reductions. But you say if there is a distinguisher that actually distinguishes between random and pseudorandom functions, then there is an algorithm that breaks a certain hard problem. For example, factors numbers. Right? So in other words, if the problem is hard, the construction is secure. This is the bread and butter of theoretical cryptography. And this is how we do things. Another way to put it, in the words of the incomparable Silvio Micali, is science wins either way. Either your construction is secure, thumbs up, or you found an algorithm to factor numbers, the open problem since Gauss, thumbs up. Well, thumbs down for certain people, but never mind, it's thumbs up as a whole. Right? That's what we do. Despite all this beautiful theory, these constructions, pretty uniformly, this class of constructions, are too slow to be used in practice. Why? I don't know. I mean, that's how it turns out to be, and they are never used. This is not for lack of trying. There were valiant efforts to speed up the fastest of these constructions and, sort of enter it into competitions to pick the pseudorandom functions that we'll use in practice. They never made it past the first round because they were 5 times slower than the competition. 5 times, you say? Well, for us theorists, it's order of 1, right? But this is what sort of has killed all these sort of nice, beautiful constructions, prevented them from being used in practice. So that's not for trying. We've tried quite a bit. Doesn't seem to have worked. What do people do in practice? Here is a construction. Here is a pseudorandom permutation construction called the Advanced Encryption Standard, which I'll describe in great detail as we go along, that everybody uses in practice. Like every second, billions of things on the internet, transactions on the internet happen encrypted with the Advanced Encryption Standard. This is the core of security on the internet. I'm not exaggerating. So pseudorandom permutations are also called block ciphers in this world. This is just the different tomato, right? But it's just a reflection of the set of people, the different set of people who study these things. So AES is fast already to begin with. It has been made faster because people have sort of built sort of chips. Intel has built a chip that has an instruction that says, look, AES encrypt this in hardware, and it's super fast. It's used to encrypt communications. It's used to encrypt the disk, for secure storage, et cetera, really used all over the place today. And consequently, it has a big target on its back, right? So this is one algorithm that one construction that if you break, you will either be very rich or you will be killed fairly immediately. I don't know which one is, yeah. So it's a very it is used all over the place that it's really, it has a target. Okay, so the question is it secure? Is AES secure? Isn't that the billion-dollar question? And the answer so far that we have come up with as a community is we don't know. We don't know. I'll tell you more about what that means in a second, but this is roughly speaking the state of affairs. So to tell you what this means and why, I have to tell you a little bit about what AES looks like. Now, this is something that we have never really, I've found very few sort of graduate cryptography classes in the world that have taught the AES construction, partly because we think of it as a giant mess of things, very ugly. Who wants to really think about it? So hopefully one thing I would convey to you is that that isn't the case. There is actually mathematics here, interesting mathematics, and hopefully you will agree with me that it's beautiful mathematics. All right, so how does AES look like? So here is the beginning of, let me see if I can, it doesn't matter. So AES is the so-called key alternating cipher. What that means is the following. It takes as input an n-bit string, right? XORs the input with the key, the random n-bit string k0, right? Applies a permutation to this, not the permuting coordinates, but really a permutation from n-bit strings to n-bit strings, yeah? That's pi. Everybody knows what pi is. It's public. There's nothing hidden or secret about it. Typically, pi is also invertible easily. There's no hardness here. So yeah, that's one round of this construction. You repeat, and you repeat, and you repeat, and you repeat until somebody says, okay, you know what? I think this is secure, and that's that. Okay. You repeat it for R rounds. And I'm going to, at the end, also XOR with a key, because if I didn't, there's no point in having the permutation pi. Anybody can sort of invert it and peel it off, right? So the bookends, there are keys XORed. They aren't in the real world, in the real construction, but for now, I'm going to say they are independently valid. That's another can of worms. So for now, the rest of the talk, KIs are independent n-bit strings, random n-bit strings. Right, so this is a key alternating cipher. In AES, the number of rounds is 10 to 14, depends if you care about that sort of thing, depending on the version of AES. So AES is actually not, is a special kind of key alternating cipher called the substitution permutation network. And the difference here is how the permutation pi looks like. Because it's not a sort of just an arbitrary n-bit to n-bit permutation. What it looks like is the following. The permutation takes the n-bits and it divides it into blocks, chunks, right? B-bit chunks, k of them, so k times b is n, right? It applies a function, a permutation s to each one of these chunks. So this permutation s is something that goes from b-bits to b-bits, right? It's typically very easy. We'll see it's actually the inverse over the finite field of size 2 to the b in AES. It's very simple, invertible, no hardness here, right? And then follows it by a linear function m from f2 to the b to f2 to the b. Right? It's a full rank linear function m. So again, it takes the input, it applies local nonlinear permutations followed by a global linear permutation. That's how the pi looks like in AES. Yeah? So far, so good? You one with me? Right. So what does this box look like? In AES, this is the inverse function over f2 to the b. Of course, 0 inverse is 0. So I say, well, that's what it is. Another way to write it is x to the 2 to the b minus 2. It's exactly the same thing. Yeah. The mixing layer is a matrix, right? It's a linear transformation, so it's a matrix over f2 to the b, right? And it has certain properties. The way it's built in AES, more or less, is that it has this maximum branch number, or the MDS property. And the MDS property says that if you look at x and m times x, the input and the output to this linear transformation, one of the two should have large Hamming weight. Rather, the sum of the two should have large Hamming weight, right? So that's exactly what. You can build these things from MDS codes, like Reed-Solomon, for example. So that's how AES looks like. Now, this is a matter of aesthetics, of course, but how many of you think this construction is beautiful? Seriously? It is a pretty natural construction. So much algebra here, right? It is not doing bit operations on some complicated things. Really, linear functions followed by inverses over the finite field. I mean, come on, it's very pretty. In fact, it's even, you don't even need to know. Well, you need to know a little bit, but you don't even need to know that much number theory to understand it. I could explain it to my 5-year-old and not have her scream out and run out, right? I mean, plausibly. Okay, so I think this construction is beautiful. And the question is, what do we know about it? What can we prove about it? Okay, so here's the bottom line. If you look at each round of AES, it is very weak, right? It is a linear function. You can invert it, right? It's public. You can invert it. It's inverse over a finite field. You can invert it. There's no hardness. There's no cryptographic hardness at all in each round, right? And yet, somehow, when you repeat it again and again and again for sufficiently many times, it becomes, hardness emerges out of what? I don't know, out of nothingness, right? Out of iteration, right? That is fascinating, right? You know, this idea didn't just come out of, this is not just AES. If you go back all the way to Shannon, he had this idea of confusion and diffusion. So somehow you do two operations, locally very complicated operations, and some sort of a mixing, just, I guess, diffusion is what he called it. This is sort of a construction along these lines. It's very natural. Hopefully I'll make some of you converts at the end, but we'll see. Okay, but suppose I want to prove the security of AES, okay? How do I get started with this? I mean, I need a hard problem like factoring to start with. I don't know what the problem is here, right? Everything I'm looking at is easy to compute, to invert, all that, right? So we, as a community, we have not found a way to even get started with this question of, you know, how do we prove the security of AES? Which one again? Yes, yes. Yeah, absolutely. Yeah, it has to be, right? Absolutely. Everything is, yeah. So the KIs are, yeah. The KIs are the only unknown things, but the way I'm using them is so simple. I'm just adding it to. So if I had a pseudorandom generator to begin with, right? I would be happy. Maybe I can somehow do GGM-like things to boost it. But I don't know what a pseudorandom generator is here. Oh. Okay. Total. Absolutely. I completely agree. Totally agree. But I don't know how to use the fact, that fact, in a proof of security. Exactly. No, Avi is just saying there's a small family, and I'm picking a function, an unknown function from this family, right? So there is that for sure. But there seems to be a gap between that and actually proving security, and I just don't know how to get started. Give me 2 minutes. 2 minutes. 2 minutes. 5 minutes. No. Who cares between us? You know. Yes, absolutely no idea, right? Okay, so how do you argue that AES is secure? That's really the question. And you know, people have, of course, looked at this question extensively. from two lenses. One, the lens of cryptanalysis. So let's just try to break it. Let's try to recover the key or distinguish a bunch of outputs from random and so forth. Lots of work, lots of techniques from this cryptanalysis world. Interesting techniques. The best attack we know is a 4 times speed up over brute force search. So of course you can sort of search over all possible keys, right? But that's essentially the best we know. Yeah, I don't even know how one computes this because it's 128-bit keys. You do something, I don't understand what's going on. But 4x, okay, let's give it. But 4x is not very meaningful. The other thing that people have done is sort of said, look, let's assume that the S boxes or the permutations pi in the case of key alternating ciphers are random permutations, random but public, right? So random, but everybody has access, Oracle access to these permutations. Assuming it, let's try to say that the construction itself is a sort of random permutation, right? So it's sort of like, it's taking a random permutation and building another random permutation out of it, which is uncorrelated. So that's nice, except the point is, in the AES construction, the S box doesn't look like a random permutation at all. Very far from it, right? So what these theorems say about the reality is unclear. I mean, they are interesting in the sense that they look at a certain class of attacks which are agnostic to the description of the S box somehow. They only use sort of input-output access to it. They do say something, but I mean, if there is an attack, I expect it to come from the algebraic structure. This is rich algebraic structure of the inverse function and the linear functions, but that's not something you capture here. Good. So back to Avi's, what Avi anticipated. Another thing you could say is to prove formally the security of these constructions against restricted attacks. Right? So T-wise independence is one example. Low-degree polynomials, can you sort of distinguish A from B with low-degree polynomials is another question you could ask. So that is sort of the point of this this line of work. And one thing you could hope to do is to, through this framework, capture the things that people have done to break certain ciphers, right? With this whole class of attacks, can we sort of capture them with a sort of like say, if this construction is T-wise independent, then none of these attacks would work. This is the sort of thing we want to say, right? So T-wise independence indeed sort of fools the class of attacks that people have, used in practice to break other ciphers. Two-wise independence already fools differential attacks and linear attacks, it turns out. Differential attacks are attacks that look at pairs of inputs, and they look at how correlated the inputs are, the output difference is compared to the input difference. So for a given input difference, can I detect some pattern in the output difference, right? So that's the kind of question you ask. And that already is fooled by two-wise independence, or even almost two-wise independence. Yeah? So this is the kind of question we want to ask. Yeah. So this is information theoretic, right? I mean, I am not making any assumptions. This is a type of guarantee that I could prove information theoretically. Of course, given sufficiently many rounds, I need the entropy of the key to be bigger than sort of essentially T. I want to T times N if I want to prove T-wise independence. So that is a sleight of hand that I will do, but it is saying something about resistance against particular attacks. Yeah, so T-wise independence, we all know, I assume, what it is. So again, you want a family of functions which have the guarantee that for any inputs x1 of xt distinct, so these are permutations, so x1 of xt are distinct. I look at the outputs y1 up to yt. I want them to look like IID random and distinct values. So random and distinct will not matter so much because 2 to the n is going to be much larger than t, so I wouldn't really worry about it. Okay, so this is what I want. It's a particular formalization, right? For every x1 of xt, the variation distance between y1 up to yt and uniform should be small. So again, this is only feasible when I have enough entropy, right? I need the total length of the keys to be at least t times n. So in other words, that means that the number of rounds has to be at least t, right? So that's I need that. So yeah, that's what it is. So, so I want to make the point that this is something, the study of, we have studied t-wise independent functions and permutations and almost t-wise independent functions and permutations a lot in computer science, right? Starting from the 80s, Luby's work, et cetera, lots of work constructing these things with optimal parameters. My goal is different here. My goal is to look at a family of constructions which are provably almost t-wise independent. So I want to come up with a proof that they are, but also plausibly pseudorandom. So if you think about the first construction that comes to mind using polynomials, right? Degree t, they are t-wise independent, but definitely not t+1 wise independent, but definitely not pseudorandom. So I want to look at constructions that are plausibly pseudorandom, in the sense that there are known attacks. So that's a goal. So this is what we show. I'll just sort of describe our results, the theorem statements, and maybe show a proof or two, depending on time. Good. So here is our result on key alternating ciphers. Says that if you want R-wise independence, right, you just need to run the key alternating cipher for R plus little o of R rounds. And that works for almost all permutations pi 1 up to pi r. No, actually it's tight, right? Say again. Because my alphabet size is n bits, right? So I can only hope to get R-wise independence. So if I run this construction for R rounds, right? The total length of the keys is R times n, right? My output length is times n. That's so the best I could hope to get is R here. We lose a little bit. So this is an existential result in the sense that we don't sort of point to a set of permutations and say, look, these guys are good. Say most permutations are good. No, this is not. This is not. This is when you instantiate the pi 1 up to pi r in the construction with some permutations. And I say, well, for an overwhelming fraction of the permutations that you instantiated with, you're good. So at least that gives a sort of a, it is probably useless in practice, right? But it gives a sense of that this construction is not horribly wrong. Coming up, 2 minutes. Okay, so to do that, to get to Mark's question, let me specialize to the substitution permutation network, where this is the pi, right? A pi applies local permutations S and then a global linear function. So let me specialize to that. Indeed, let me specialize to the case where S of x is either x inverse, which is used in AES, exactly what is used in AES, or the cube function, which is used in a different cipher called memc. Okay, and let's say my mixing function is nice in the sense of MDS functions. So here's what we show. We show that if you run this construction for 2 rounds, which I think means 3 XORs, which is like 1 less than what is shown in the picture, you already get 2-wise independence, almost 2-wise independence, which is with these parameters. I don't really want you to parse the parameters, right? It's just something reasonable. As B becomes large compared to K, you get something non-trivial. You need B bigger than K for that to be non-trivial. If you iterate for 1 more round, you get better 2-wise independence. So this is K over 2 to the B, and this is 2 to the K over 2 to the B. So you get better. And if you iterate for 6 rounds, so this construction, the reason we are going forward at all is because if you plug in the AES parameters, K is 16, and B is 8. That turns out to be 1, which is not cool. So let me run it a few more times, okay? Why not? I did a 2, I did 3, why not do 6? Then I actually get something reasonable. Why 0.472? I shouldn't be happy with it, right? Now there is this fantastic theorem, amplification theorem of Kaplan, Maurer, and Reingold back in the days, and Maurer, Herzog, and Renner. I think they discovered it independently. Which says that if you take 2 permutations, both are close to 2-wise independence, generalizes to T-wise, the composition is better, is closer to 2-wise independence, right? Composition means look at a family of functions, which is f composed with g, f taken from matcap f, and g taken from matcap g. Point for 1 layer, 1 level. One round doesn't work, like provably doesn't work, it turns out. What do you mean? 2 to the 128 square. I wish. We actually did some shenanigans of this form for 16-bit functions. You know, like we have an undergraduate student. Thankfully, the guy knows how to code. You know, for me, you know, it's and he did do this for 16-bit versions of these functions with GPUs. Okay, so if you apply this theorem, so this theorem requires that number to be less than 1/2. Otherwise, you won't get any amplification here. But if you do, then the right thing happens. Okay, so never mind the parameters. I think the point is the qualitative point. Okay, so this is what we can show for 2-wise independence, right? So it's already something. How about the two questions that come out of it? What about T-wise independence? And what about, this is a question that's interesting from practice, can you give meaningful bounds on how many rounds you need to run to get 2 to the minus 128 close to random? This is something that practitioners would ask me, right? The answer for, if you plug in the bounds from the previous theorem is 1,000. This is some thousands. Some obscene number of thousands. So it turns out that both can be improved. You can actually prove T-wise independence in a sense that I'll tell you in a second, and you can get the number of rounds to be much smaller, of the order of hundreds. And just to give a reference, 100 or so. Just give a reference in the AES construction, the number of rounds is 10. It's a factor of 10 from where it is. Okay, so answer both these questions. Slight variant of AES, and I'll tell you about that if I have time. All right, so let me go back to this theorem and sort of give a flavor of how to prove it, right? And again, you know, this is my mathematics here. This is cool mathematics, in my opinion, here. Right? All right, so again, the AES construction, right? Which is a thing on top, right? So you take an input, you apply you break it up into bits, break it up into blocks of size b. You apply the inverse function to each block. Then you mix it up with the linear function, rinse and repeat, right? That's the XOR the key and then rinse and repeat, right? That's what you. All right, so the first observation, so again, what do I want to prove about it? 2-wise independence, right? So I look at 2 inputs, x1 and x2, and I look at the outputs y1 and y2 and say, well, you know, can I prove that the distribution, the joint distribution of y1 and y2 is uniformly random? It's close to uniformly random. That's the question, right? So the first observation again is that it's enough to argue not about the joint distribution of y1 and y2, but the XOR of y1 and y2, the difference between y1 and y2. That is because if you look at the marginal distribution of y1, it's truly random because I'm XORing with the key at the end, the random key at the end. So the marginal distribution is truly random of each one. So the only thing that matters, really, it turns out, is XOR of the two. Right? So that's enough it's enough to show that. Yeah, so y1 and y2 are uniformly random, subject to the difference being the same as the thing before XORing. All right, so let's try to understand differences. So that seems to be the name of the game here, right? So let's take some pair of inputs with a certain difference delta, right? So x1 and x2, whose difference is delta. Difference is XOR between the two. Yeah, because we are working with field of characteristic 2. Yeah, so x1 XOR x2 is delta, and let's fix delta and see what happens to y1 XOR y2. How is it distributed? Is it fixed to something? Does it have randomness? Good. So again, what I want is this probability, right? So I pick two random inputs whose difference, XOR difference, is delta, right? So x and x plus delta. X is random here. I'm interested in the difference between s of x, which is x inverse, and s of x plus delta, which is x plus delta inverse. That is what I asked. How is it distributed? Now, this is a clean mathematical question, right? I mean, I could ask you as an exercise. In fact, I do class, right? And you know. So here is a theorem that one can prove. This difference, right, is uniformly distributed on a set of 1/2 2 to the b delta primes. So so I ask, what are the possible values of s of x plus delta? There are 2 to the b minus 1, 1/2 2 to the b possible values, and it's uniformly distributed on them. I'm actually lying here, but epsilon lies are okay, right? I'm almost telling the truth. That should be okay. Yeah, so this is something very, very cool, right? And I know precisely what delta primes actually appear. This scary looking condition on the trace of 1/delta times delta prime. If it is actually 0, then delta prime is a possible difference that appears. Otherwise, it isn't. So let me sort of demystify this a little bit. Why trace? Why does it come up? So one point I want to make before I move ahead. This is not uniformly random. The set of all differences in the output, delta prime, is not uniformly random. It is uniformly random on a subset of size 1/2. Can anybody sort of see why that must be the case? I mean, you could say, maybe this is something wrong with the inverse function. You should be using something else. But that isn't. I mean, this is the best I can do. Anybody say why that must be the case? After one round, sort of like Mark's question, I cannot get uniformly random. This expression is symmetric, right? The difference expression, s of x plus s of x plus delta, is symmetric. So if you plug in x plus delta instead of x, you will get exactly the same value, right? So the function mapping x's to possible differences is a 2-to-1 function at the very least. Right? So the number of possible output differences that can appear is at most 1/2 the number of possible x's, which is 2 to the b. So this is the best you could possibly do, and the inverse does the job. Okay, so let me sort of demystify this a little bit. Why does this sort of thing come up, right? And it's fairly elementary algebra. Let me see if I can. Good. It's a very simple claim, right? This is what it is. Let's write down this expression, right? S of x, which is x inverse, and s of x plus delta, which is x plus delta inverse. Let's write it up. And what do you see on the right? Voila, a quadratic equation. You see the quadratic coming up, x times x plus delta, right? Yeah, so 1/x plus 1/x plus delta, you have x times x plus delta coming up in the denominator. Now you do mathematics, you do arithmetic, really, right? It turns out that this guy has a solution. This guy has a solution in delta prime if and only if this guy has a solution. So this is a quadratic, right? This is just a right-hand side. So for every delta prime for which this guy has a solution, old guy has a solution too. This is just manipulating equations. And that is, it's just completing the squares, except you're in characteristic 2. You cannot complete the squares, but you do what you have to do, and that's the condition. That's it. Okay, so there's nothing, yeah, I mean, it's a very natural sort of condition that comes up. All right, so again, we are at the point where we want to understand differences, right? So how do differences, input differences, propagate to output differences? Okay, so this is the game. So given an input difference, what is the distribution of output differences? What we just saw is that for every non-zero input difference, the output difference is distributed uniformly in a set of size 2 to the b minus 1. So it's not uniformly random, but it is pretty close to it. It has entropy b minus 1 bits. Okay, so high entropy b minus 1 bits, but not uniformly random. So one round doesn't give me anything. But what's the next question you should ask at this point? What happens if I do one more round? Right? And the analogous question there is, what if you choose delta itself to have high entropy, b minus 1 bits of entropy? That's what happens in the next round, right? Yeah. So this is what we show. So this is sort of turns out actually to work out. Why? Because of a couple of lemmas that we prove, sort of extraction lemmas, essentially. So think about this experiment where you have delta 1 up to delta k, right? So now you have parallel repetition of these things, which lead to delta 1 prime up to delta k prime. And what we show is that if each delta I has lots of entropy, but they could be correlated, right? So, you know, delta 2 might be completely determined depending on delta 1, right? Then this guy is close to uniform. So sort of like you have b minus 1 bits of entropy, and then you add a lot, right? You add a key, really. Then you get really b minus 1 bits in each of the, well, you get uniform b bits in each of the coordinates. Because, yeah, exactly. So the randomness actually comes from the key that I'm going to add in the next round. Exactly. And you can do this. You can prove a stronger version of this lemma, which says that if delta I are not just individually random, but they are sort of a block source, if you will, right? If every set of size I has entropy I times b minus 1, let's say, then you can prove even better parameters. So let me sort of say where this is. What is the sort of the brain underlying all these things? And this is a very simple subspace sampling lemma, which looks at the following game. Let's pick delta from a distribution with large entropy. Let's say b minus 1 for a moment. And I'm going to pick delta prime to be a uniformly random vector, which is orthogonal to delta. Why orthogonal to delta? Because of that equation, right? I know not just the distribution of the entropy of the distribution of delta prime, I actually know what the distribution is, right? So 1 over delta prime, if you look at the set of all 1 over delta primes that come up, they form a subspace because of the additivity of the trace, right? Trace of x plus trace of y is trace of x plus y, right? So if 1 over delta 1 prime appears and 1 over delta 2 prime appears, then the sum appears as well, right? So the additivity says that, you know, you're really kind of picking from a subspace of dimension b minus 1, right? So again, saying, you know, and let's say that subspace is orthogonal to delta. It doesn't matter up to permutations. It doesn't matter, actually. It turns out you can do this. So again, you have a distribution of delta has entropy b minus 1. Pick delta. Then pick a uniformly random vector orthogonal to delta. And the question is, what is the distribution of this delta prime conditioned on delta? That we show is uniformly random. There's lots of entropy here, right? I mean, there's 2 times b minus 1 bits of 2 times b minus 1 bits of entropy. So, you know, like I'm not making stuff up. This just says that you're not like being stupid with entropy. Okay, the proof is elementary Fourier analysis. If you just write down what this is, you'll get it. Okay, so let's put it together to a proof of security of 2-wise independence. So you start from an input, which 2 inputs, which are different somewhere, right? Let's say in the middle block here. They have to be different. Otherwise, the construction will produce the same output, right? You run it through one iteration of this construction. What do you get? 0 stays 0. 2 blocks are the same. Well, they'll remain the same after you run it through SBOX. Otherwise, you get a difference, which is entropy b minus 1 bits. Now you run it through the mixing layer, right? That ensures that each block has entropy b minus 1 bits. So it sort of diffuses the entropy into all the blocks. Of course, these blocks are going to be correlated, right? But each one has entropy. Now you run it through another iteration of the S box. The extraction lemma, the weak extraction lemma, says that each one will be uniform and independent. The collective distribution will be uniform and independent. That close to independent, that comes in because we union bound over all subsets of size k. Okay, and that's that. That does the job. Now, how about 3 rounds? Well, you start from here where one of the blocks has entropy, and then you pass it through the mixing step, and all the blocks have entropy, but they're correlated. Now you observe that the fact that they all have entropy means that none of them are 0 with high probability, right? All of them are non-zero with high probability. Yeah, so the probability that each one is 0 is like 1 and 2 to the b minus 1 times k, right, by union bound. That's the probability that any one of them is 0. As long as that is small, none of them are 0. Now you run it through one iteration of the S box, which gives you entropy, which gives you uniform randomness, right? So each subset will have entropy at this point. And then again, another iteration will tell you that really the whole thing is uniformly random. This XOR is the key before, yeah. So sort of the details matter, but the high level picture is sort of like a way to say one iteration of this construction does something, and that something is nice enough that you can induct on it, right? So how do I, okay, let's see. Okay, so let me tell you a little bit about the t-wise independence beyond t equals 2. Okay, so let me stop here for a moment. So can we take a breather, maybe? All good? Yes, Mark.
DS, like you mentioned that.
DS, yeah.
Turned out to be protected against differential attack.
No, DS was broken by a differential attack, as far as I remember.
The one that was in, so wasn't there a story that was privately known?
Insecure against differential cryptanalysis? Maybe, I don't know, but eventually it was broken with differential cryptanalysis, Biham and Shamil.
So AF was different from differential attack.
Not provably so, right? I mean, it was, there were all sorts of heuristic sort of arguments for why differential attacks shouldn't work, but they're all like, you do things that you shouldn't. You assume things are independent when you clearly shouldn't do it, right? So I don't know. I think there was some sort of a nice, warm and fuzzy feeling that AES is secure against differential cryptanalysis, but I don't know proof of that.
Differential just means pairs.
Pairs, yeah. No. Just pairs, right? And t-wise independence would tell you something about t bigger than 2, will tell you something about triples, right? And that was just, I mean, that wasn't even in the radar somehow. All right, so let me keep going for a bit. t-wise independence. Right, so we're going to answer this. We are not able to answer this for AES itself. That's unfortunate, but we answer it for a slight variant of AES, which hopefully, you will agree with me that it's natural. All right, so this is AES, right? This giant construction, but you should just look at one. I mean, if this is scary, just look at here, okay? Just one copy of it, and then the rest of it is the same. We look at censored AES. So what is censored AES? I'm going to remove some of these mixing layers, just throw them away. They're identity functions, okay? So this guy goes away, this guy goes away, etc., etc. So I throw away a whole bunch of mixing layers, and then I keep one. Then I whole bunch and then keep one, etc. Right? This should only hurt security, right? I'm mixing less. I mean, this is again warm and fuzzy, right? There's no proof. This should only hurt security. So if I can prove this secure, then the old AES should be secure too. I don't know how to prove that, but we conjecture it, right? So there's a censoring conjecture that says if censored AES is device independent, so is the original AES. I just don't know how to prove it. Okay, but we'll look at the censored construction from now on. All right, so here's how the construction looks like, right? So I iterate a whole bunch of S-box XOR with key, S-box XOR with key. There's no mixing in between, right? I do it in parallel, then I have a mixing. And then I do this, so on, right? So this is how the construction looks like. So I'll prove that this is device independent in 2 steps. The first step, I'll just look at one of these boxes. You know, this guy, which is, what is it? It's apply the inverse permutation, XOR with the random key, apply inverse permutation, XOR with the random key, keep going. What can you say about this? Say again? Beautiful. Beautiful. So this was actually, a version of this was known from an old result of Leonard Carlitz from the 50s, it turns out. He didn't prove that this will converge to random, but rather that you can hit every even permutation with sufficiently many repetitions of this in this process. Right? So this is actually a generating set. The set of all affine functions is what he showed, together with the inverse permutation is a generating set for the alternating what he showed. Right? It's a very clever proof. It's a 1-page, half a page actually proof, super clever. So we sort of extend it and we say, look, this actually converges to random in about the same number of steps that, in about the number of steps that you would expect, which is 2 to the b, right? B times 2 to the b. Good. So that's 1, right? So this becomes random. For him? No, not as far as I know. It was just sort of studying generating sets of finite fields, you know, of symmetric groups acting on finite fields, right? He didn't say anything about anything cryptographic there. Yeah, right. That's that. Because you want a random permutation from 2 to the b to 2 to the b, right? B bits to b bits, so 2 to the b, right? So the total number of permutations is b times 2 to the b factorial, right? Log of that is b times 2 to the b, right? Yeah, b times 2 to the b, yeah.
How many? How much? So you put the principal to p rounds or not?
Not p rounds. 2 to the b, 2 to the b bits, roughly speaking. So I'm asking for a lot here, right? I'm asking for this this composition to be a truly random permutation over 2 to the b. I don't need it. I only need it to be t-wise. I only need its action on any t elements to be random. That's all I need at the end. So I'm overdoing it here, right? Overdoing it for blocks. Exactly. It turns out that this inverse function is bizarre in the following sense. If I repeat it for like 4 rounds or something, it becomes 2-wise independent. If I repeat it for 10 rounds, it is not 4-wise independent. It's not 5-wise independent. It's not 3-wise independent. It just breaks down for a reason that I can explain offline. But suddenly, if you repeat it for 2 to the b steps, it becomes truly random. So there's sort of a phase transition phenomenon going on. And not for few, relatively few steps, right? If I 2 to the b is the size of the generating set is 2 to the b, right? Because it's all affine functions, all linear functions, let's say. But we are talking about two different random walks, right? So this is the random walk over the symmetric group, right? And you're right. I mean, it has spectral gap. It has constant spectral gap. I want to reach 2 to the b factorial elements with a degree 2 to the b. So roughly 2 to the b steps suffice. The other random walk I'm talking about is not on the Cayley graph. It's on the Schreier graph. Sort of actions of permutations on T elements, right? So in 2 to the b steps, of course, that'll converge too. But what I want is that in t steps, if t is much smaller than 2 to the b, I expect that it'll converge in about t steps. It doesn't. I can tell you the reason, but offline. The point is that this function x inverse is a rational function. So if you repeat a rational function composed with an affine function many times, it's still a rational function. You know, it shouldn't have that much randomness to begin with, right? Until it hits a 0, and then you cannot invert it, and now it becomes it's something interesting going on here. But we can take that offline. Okay, so anyway, so we show this, and then the problem becomes actually understanding, you know, this SPN thing where each S box is truly random, because that's what we just showed, right? This composition of these guys is close to truly random. That's it. And that's the next thing. So this is sort of what we show, but I don't want to get into numbers. I want to sort of show you the qualitative. Good. So how does one show this, right? A random S box has the following property. If the input difference is 0, the output difference is 0 as well. It's a permutation. If it maps, yeah, I mean, otherwise, the output difference becomes truly random, right? That's what I get. So that lets us define a graph on the set of layouts. A layout is the set of vertices is 0, 1 to the k, the set of all k-bit strings, and the ith bit is 1 if the difference in the ith location is 0, and 1 if it is non-zero, right? So there's a set of all sort of differences, whether they are 0 or non-zero. Good. So you take any input with a certain activity pattern, you pass it through the S box, you get a random input with the same activity pattern, because 0 stays 0 and non-zero becomes truly random non-zero. And so this is what it looks like, right? You have a graph on layouts. Each application of the S box in parallel takes a node to a random node inside the layout, and the mixing step takes it to potentially a different layout, hopefully. Now all you need to analyze is this graph. That's that. And yeah, indeed we do, and we get what we get. All right, so this is all I wanted to really say. A little bit out of time. I think this question of okay. So first of all, I'm sure it's in the eye of the beholder, but I am the beholder here. In my eye, it's beautiful, this construction. And I think understanding the security is a foundational question in cryptography. It's beautiful mathematics, lots more to be done. We are just sort of scratching the surface, I think. Clearly, there are sort of like obvious connections to random box. There have to be more that one can do here. You know, I am bounded by my ignorance, right? Lots of open problems, security for NET, more complicated attacks like algebraic attacks, like low-degree polynomials. Can they distinguish between one and the other? You know, AES and random. Lots of open problems. Here's a concrete one, which I don't know how to show. You let the S box be the cube function, right? And you repeat it, you know, about t steps. I want this to be a t-wise independent permutation. That's my conjecture. I don't know how to show it. At the end of the day, it reduces to showing the spectral gap of a certain random walk, right? Yeah. Question is how to do that. For the inverse function, this is false. This is the conversation with Avi, right? I know how to show that this is 2 to the b wise independence, in other words, a truly random permutation in about 2 to the b rounds, but I don't know how to show it for a small t smaller than 2 to the b. Other directions. So let me just close with mentioning two other directions one could pursue here. We are stuck. We don't know how to reduce the security of AES to any concrete, simple mathematical assumption. Short of saying the construction is secure, we don't know how to do it. What we did is a bit of cheating if you think about it, right? To prove device independence, I needed to increase the number of rounds proportional to T. So I can't. I mean, it's not AES. It's AES has 10 rounds. It can at best be 10 wise independent. Yeah. Different research direction. This is motivated by a conversation with Charlie Rakoff. Is do physics, not mathematics. In physics, what do people do? They can't prove anything. I'm sorry. Is it recorded? I hope not. Is it recorded? Never mind. You come up with theories, right? You come up with conjectures, and you try to falsify them. Charlie's conjecture says that if you take any simple, with simple can be interpreted the way you want, 4-wise independent permutation, you iterate it sufficiently many times, it becomes pseudorandom, cryptographically pseudorandom. Falsify it, you know. Yet another direction is to come up with new design paradigms. I mean, AES is one kind of design where iteration of many simple functions gives you randomness. There are at least two other ones I can think of. One by Gowers, actually. So he looked at this question of you have n bits. In each step, you pick a random function, 3-bit function. Okay, one that takes a random three bits out of n bits. You apply an invertible function to these 3 bits, right? Then you repeat it. Pick another set of 3 bits, apply a random 3-bit function, keep going. So the key in this construction is a sequence of all random 3-bit functions, like little truth tables, right? Does it converge random? We know actually answers here for device independence. Yeah, I think there are really fascinating questions here, not just in the direction that I said, but also in these directions. So thanks.
We have time for maybe a few questions.
Sorry for running over. Yeah.
The other direction. The one iteration is not through the 2 iterations are not secure?
Well, it depends on what you mean by secure, right? 2 iterations are pairwise independent of the AES function itself, close to pairwise independent. We can't prove particularly good closeness, right? You know, the pretty bad parameters. Those parameters improve if you iterate it 3 times. The closest that our theorem is tight? No, we didn't try. We didn't try. It's plausible. It's plausible that our theorem is not tight. You just put it that way. Yeah.
This is like a little bit about whether like plans to understand why AES might actually be a good idea. Is there like some motivation that at least in retrospect you can give for why we must choose S of X as
inverse? Okay, the only explanation I've heard is that it's an involution. So they want to build a circuit that computes it. The same circuit should invert it as well, which it turns out is, I mean, well, it doesn't come across as particularly compelling to me, but that's one reason I've heard. I'm sure there are others. The fact that if you propagate a difference through the inverse, right, you get really the uniform distribution on the set of all half the set of differences. That's a good property. That sort of says it's maximally sort of diffusing in a certain sense. That could, yeah, that could probably be it. But I've never seen this articulated I've never seen this articulated in even a somewhat formal way. Thanks.